Well, we're almost done with our chapter on identities. We're going to talk this time, though, about double angle identities. So I'm going to take a few minutes and I'm going to actually show you how you can derive these identities if you're given a little bit of information. So when we talk about a double angle identity, let's suppose that I have two angles, two separate angles, but they happen to have the exact same angle measurement. If I let the cosine of A plus B, right, that would be our sum of two angles, then I can rewrite this as the cosine of A plus A because we're saying that A and B are equal. So I rewrote this using that assumption up here. And we can then use our sum identity for cosine to rewrite this so that it's going to look like the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. And now let's simplify. Cosine A times cosine A would just be cosine squared A. And the same for here, we'd have sine squared A. So what I end up with is really the cosine of 2A equals cosine squared A minus sine squared A. And that's going to be our first double angle identity. Well, just like previously in the sum and difference identity for cosine, we have other forms that cosine can be written in. So we want to look at that as well. So if I have the cosine of 2A, which we said was cosine squared A minus sine squared A, I'm going to rewrite this. I can rewrite the cosine squared A using the Pythagorean identity. And it would look like the cosine squared A is 1 minus sine squared A. So we're going to replace this with 1 minus sine squared A minus the sine squared A I already had there. And let's simplify this. So I have 1 minus 2 sine squared A. So that's another form that I can see the double angle for cosine in. And there's even one more where we're going to replace sine squared A. So let's do it one more time, just so you can see what's happening. Minus sine squared A. This time we're going to replace this with, again, the Pythagorean identity. That thing comes in handy, let me tell you. 1 minus cosine squared A. So 1 minus cosine squared A. But we still had cosine squared A here. Now I'm going to distribute, so I get cosine squared A minus 1 plus cosine squared A, because a negative times a negative is a positive. And when I collect my like terms, I have 2 cosine squared A's minus 1. Now I'll show you in a minute all of these identities summarized, but that's how you could derive just the cosine double angle identity. Let's do the same thing for sine. Again, we're going to let A be equal to B, and we're going to start off this by saying, well, if I have the sine of A plus B, then I can rewrite that. So it's the sine of A plus A, because I'm letting A and B be the same values. So this is now the sum identity for sine. So we have the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. And both of these terms are actually the same thing, so I really have 2 sine A cosine A's. So sine is a little bit easier. We can see that the double angle for sine is pretty fast. It comes out like this. Let's do one more with tangent. You'll see what I'm talking about. If, again, I let A be equal to B, and I'm going to start off with the tangent of A plus B, I can rewrite that as the tangent of A plus A. And using the sum identity for tangent, we have the tangent of the first plus the tangent of the second over 1 minus the tangent of the first times the tangent of the second. So we're just going to clean this up, and it ends up looking like 2 tan A over 1 minus tan squared A. And that's what the double angle for tangent happens to look like. So down here in this box, you can see that I have those identities summarized. You're going to want to make sure that you get that written down. So we're going to go ahead and we're going to look at this first example right here. This example is similar to the examples we've done in every other section where we're given some value for sine or some trig value, and it's other information is telling us what quadrant it's in. And since we're learning about double angles, we're going to try to find the sine, the cosine, and the tangent for 2 theta. Now notice that they gave me sine theta right here. Let me go back up. If I want to find the sine, the tangent, and the cosine of 2 theta, you can see in all of these that I'm going to need to know not only sine theta, but cosine theta and tangent theta to be able to plug into these identities and solve, and figure out what's being asked. So having said that, that's kind of the first thing that we're going to do. So we want to find cosine and tangent of theta, given what sine theta is here. Now we have a couple of different choices for how we want to go about finding cosine and tangent. So I'm going to show you both choices. Okay, option 1, that's what we'll call this. Option 1 says I'm going to use the Pythagorean identity. If I know what sine is, then I can find out what cosine is. Remember, that one says sine squared theta plus cosine squared theta equals 1. And if I know what sine squared is, I can replace it to solve for cosine. So we're going to say 8 over 17 squared plus cosine squared theta is equal to 1. And now I'm going to solve for cosine squared theta. So I'm going to show you, because I'm doing cosine squared theta is equal to 1 minus 8/17 squared, because I'm going to actually put this portion right here into my calculator. 1 minus 8 divided by 17 squared. I want back the fraction, math frac enter, and I get 225 over 289. So that's what cosine squared is. But I need to take the square root of both sides, and I can do that in the calculator. So I'm going to say second square root of that thing up there. And I want to do math frac enter. And it gives me back 15 over 17. So I know that cosine theta is 15 over 17, but let's go back up here because I covered it up. Cosine is less than 0, so in other words, cosine is negative. Now that's one way for you to be able to find cosine. The second way would be to use what we learned back in chapter 1 or the very beginning of chapter 2. And that's where, if I know that the sine is y over r, I would know that y is equal to 8, r is 17, and because cosine is supposed to be x over r, I can then solve for x. So that would be the square root of r squared minus y squared. Remember, that's the Pythagorean theorem. So x is going to be the square root of 17 squared minus 8 squared. Plug that into your calculator and you'll see that sure enough, that's 15. Okay, so we have a couple of different ways that we can find out what we're looking for. One way or the other, whether you use the Pythagorean identity or this other method over here, we're still going to come up with what cosine theta is. Remember though that I not only wanted to find out what cosine theta was, I need to figure out what tan theta is. So whichever method we chose to use, I still have everything I need. I know that tangent would be, let's look over here, tangent would be y over x. So that would be 8 over 15. And one other thing, sine is positive, cosine is negative. That tells me I'm in quadrant 2, and therefore tangent needs to be negative also. Okay, so we have all the components that we need to be able to figure out sine, cosine, and tangent of 2 theta. Let's do the first one together. The sine of 2 theta is 2 sine theta cosine theta. Okay, well, that would be 2 times sine theta, we are told, is 8 over 17. Cosine we just calculated was negative 15 over 17. And we're going to just multiply these together using our calculator. When you do that, you should get negative 240 over 289. Well, let's look at the cosine of 2 theta. And you have 3 choices you can choose for the cosine of 2 theta. Choose, I want you to stop the video and I want you to pick one of those cosine 2 theta identities, and you're going to fill in so that you can simplify and solve and get the value back. Okay, so go and pick whichever one of those identity forms you're going to use, and we'll meet back here and make sure we get the same answer. Okay, so I worked this using all 3 variations of the double angle for cosine. You can see it doesn't matter which one form I used, you should come up with an answer of 161 over 289. So, last but not least, let's look at this one, the tangent of 2 theta. Now remember that the tangent of 2 theta looks like 2 tan theta over 1 minus tan squared theta. Now we calculated tan theta to be negative 8/15. And that's 1 minus negative 8/15. No matter what your process is for putting that into the calculator, you should end up with an answer that's negative 240 over 161. Okay, so those are your answers for that particular problem. Well, let's look at another example down here. We want to be able to use our identities to find the value of sine and cosine. Okay, so I am going to be looking for the sine x and cosine of x. If I'm given the cosine of 2x is equal to 2/3, and that I know I'm over here in quadrant 2. Okay? So again, we are given cosine of 2x. So I have 2 choices that I can use. I know that the cosine of 2x is equal to 2 cosine squared x minus 1. I also know that it's equal to 1 minus 2 sine squared x. There's a third choice, but I'm not going to use that one. I have 2 options here that I'm going to pick from. These are the 2 choices that I could use, and the reason I'm doing that is because if I were to choose this first option, I have a 1 already there. I'm going to plug in 2/3 for cosine 2x, and that leaves me 1 unknown out of this. The same thing holds true for this one right here. If I have a 1 that I know of and I can replace cosine of 2x with 2/3, then all I'm solving for is sine squared x. Okay, So I can do that here. So let's go ahead and we're going to take the first choice, and I'm going to do that one first. So if I know that the cosine of 2x is 2 cosine squared x minus 1, and I'm going to replace cosine 2x with 2/3. So we get 2 cosine squared x minus 1. So all I'm solving for is this part right here. We're going to add 1 to both sides. We end up with 5/3 is equal to 2 cosine squared x. So I'm going to divide both sides to get rid of that 2. That's going to give me 5/6 is equal to cosine squared x. And now I want to take the square root of both sides. So I'm going to rewrite this so it looks like the cosine of x is equal to the square root of 5 over the square root of 6. So I can take it from this form here and rewrite it so that the numerator and the denominator each have their own radical symbol. That just helps me see that when I rationalize the denominator, right, rationalizing it means multiplying by the denominator, then the cosine of x is going to end up being the square root of 30 over 6. But remember, we're in quadrant 2, so this needs to be negative. Okay, so there's our answer for cosine of x. Let's go back. We can use the same identity. Cosine of 2x is 1 minus 2 sine squared x. I could use the same identity to solve for sine. So let's say I have, again, 2/3 is 1 minus 2 sine squared x. So you're going to do the same thing here. We're going to subtract 1 from both sides, and when we do that we get negative 1/3 is equal to negative 2 sine squared x. I'm going to divide both sides by 2, and I get 1/6 is equal to sine squared x. Take the square root of both sides, and I get sine x is the square root of 1 over the square root of 6, which is really just the square root of 6 over 6. So that's what sine x is. Now there's a couple of different ways you could have gone about getting this answer. I could have started with this identity over here, then used the Pythagorean identity to come up with this value. I could have started here and used Pythagorean's identity and gone in the other direction. There's all sorts of ways that I could have gone. This was just one way. I did have to have a starting point though. Okay, let's look at this next example. Again, the instructions are the same. I want to try to find the sine and cosine of, there we go. I want to use identities to be able to find the sine and cosine of 2 theta this time. And I know that sine is negative, cosine is positive, so if that's the case, then I need to be down in quadrant 4, because that's where cosine is positive. So we're just going to start. If I use the double angle identities and I'm only given sine, let's see how we can go from there. So since we know we're going to be looking for, we're wanting to find the cosine of 2 theta along with the sine of 2 theta. So the cosine of 2 theta has a bunch of different variations for me to use, but the sine of 2 theta is pretty straightforward. It's pretty strict. And when I find the sine of 2 theta, then I'm going to be using not only the sine but also the cosine of theta to give me this amount right here. So in other words, my first step I think is going to be to find cosine theta. Okay, so cosine theta, you can do all sorts of different things in finding cosine theta. Let's do the XYR. If I know that, not X, if I know that Y is negative square root of 5, R is 7, then I'm looking for X. So X is going to be the square root of R squared minus Y squared, which is going to be the square root of 7 squared minus negative square root of 5 squared, which would be 49 minus 5, which would be the square root of 44. And hopefully you remember that when I reduce this, that's going to be 2 square roots of 11, because I'm looking for perfect square factors of 44. And that's what I get right there. So in other words, the cosine of theta is going to be 2 square roots of 11 over 7. Okay, so I could have done this XYR. I could have done the Pythagorean identity. Remember, that was either one I wanted to do. Now, at this point, since I'm working with sine, I'm going to go ahead and I'm going to find the sine of 2 theta. Remember that that's 2 sine theta cosine theta. So sine theta, we already said that was negative square roots of 5 over 7 times 2 times 2 square roots of 11 over 7. Okay? This one's not as easy to do. I don't think you can do this one in your calculator because of the radicals that are in the numerator. So instead you have to remember how to multiply fractions. When we multiply fractions, we're going to multiply numerator to numerator. So I get 2 times 2, because those are the real parts, so that would be 4. And the radical parts would be 5 times 11, which would be the square root of 55 with a negative out here. And 7 times 7 is 49. So that's what the sine of 2 theta is. Now let's go back and let's see if we can figure out what the cosine of 2 theta is. Okay, so the cosine of 2 theta is going to be, we have a couple of different choices here, but let's just use 1 minus 2 sine squared theta. 1 minus 2 times, I'm told at the very beginning, in other words, I'm given that sine is negative square root of 5 over 7 squared. So when I simplify this portion right here, I should end up with 39 over 49. And that's what the cosine of 2 theta is equal to. Okay, so that's how we're going to use identities to be able to find sine and cosine, whether we're looking for sine x or cosine x.